Hi, my name is Erin Coulon.
And I'm Peyton Carter, and our project is called Testing the Safety and Viability of a Cross-Linked Starch-Based Bioplastic in Food Packaging and Food Industry Applications. Thanks to its versatility, plastic is widely used, but it is made of petroleum, which is dangerous to transport, extract, and it also causes pollution. What our project focuses on is finding alternatives to food industry single-use plastic.
So a lot of our project stresses sustainability and the ability for our product to degrade in the environment. So we followed Anastas and Warner's 12 green chemistry principles, which are a framework for sustainable development of new technologies. Specifically, we followed Principle 7, which states that the product should come from renewable sources, and Principle 10, which states that the product should not persist in the environment. So all three of the molecules that we studied, which were citric acid, glycerol, and starch, are renewable. Citric acid naturally occurs in a lot of fruits and is generally recognized as safe by the EPA. Glycerol is a non-toxic alcohol and is a byproduct of the hydrolysis of fats in the soap manufacturing industry, and starch comes from many different plants, so it's renewable. And so our project aims to examine if tapioca starch can be used realistically and safely in a real-world setting to replace the traditional plastic Tupperware cups and cutlery and other single-use type products. And specifically, we wanted to model our packaging after polyethylene, which makes up a lot of plastic bags in a lot of the food wrappers you see. So these are just some reactions between the different molecules that we studied. And we hypothesized that a combination of starch, glycerol, and citric acid will result in a stronger and more effective bioplastic due to the strong combination of intermolecular forces like OH hydrogen bonds and ester bonds.
Initially, we tested tapioca, potato, and cornstarch with 10, 15, and 20% glycerol. And after some qualitative analysis, we decided on using 10% glycerol with tapioca starch. So overall, we hypothesized that the modified plastics made with citric acid would resist heat better, they would be less susceptible to water damage, they would maybe influence the pH of water slightly, but not much because they would be more water resistant. And we also hypothesized that cross-linked plastics would be stronger mechanically. We did 3 plastics with no citric acid and 2 that were modified with citric acid with varying starch levels. The general procedure that we used to make our plastics was we would add starch and water to a beaker and heat it until it became thicker in consistency. And then we would add our glycerol and pour it as a film. And for the modified plastics, we put the plastics in the oven afterwards to allow the cross-linking interaction to occur. And as you can see, some of the plastic is dyed yellow. That is because one of our tests, the degradation test, used yellow dye to measure in the colorimeter to see how fast the plastic was releasing dye as it degraded.
Okay, so for some quick qualitative analysis of our plastics, trial 1 was bubbly and kind of sticky, and it also took a longer time to dry, along with it being fragile. Trial 2 was also sticky, and it had a slightly shorter drying time. Trial 3 was by far the closest to polyethylene that we produced. It was easy to cut, it wasn't sticky, and it dried in a short time. Trial 4 was initially tacky and fragile, but over time it became a lot more durable, and it also had a lot of bubbles in it. And trial 5 was brittle, had a very long dry time, and it formed a lot of cracks while in the oven.
The procedures of our test did take up a lot of this presentation, so the specifics of that will be outlined on our PDF and on our submitted research plan.
So the first test that we ran was a degradation test. This test was to indicate how the polymers would interact with the natural environment and roughly at what rate they would degrade. And so you can see on this graph that trial 1 degraded significantly more quickly than the other trials. So as we can see on this individual graph, the steep positive trend line indicates that this polymer degraded the most quickly, which this can mean a good thing, meaning that it won't persist in the environment, but it can also be a bad thing because this might indicate a low durability. And so this is the graph of trial 2. We can also see a positive trend line on this one, which indicates that the polymer does degrade, but compared to trial 1, it's less steep, and so that means that this trial will degrade at a lower rate, which might indicate that it's more durable than the last trial. We see a similar trend in this graph with the positive trend line. However, it's less steep than the initial trial 1 trend line, which indicates that it might be more durable. However, it degrades at a slower rate. With trial 4, we see a very flat trend line, and this is the citric acid polymer. And this indicates that it'll take a longer time to degrade in the environment, which might not be the best thing. And we see for trial 5 is also a very flat trend line. This is the other citric acid trial, and this means that it'll take a long time to degrade in the environment. The next test we ran was a mechanical test to see the amount of strength that the plastic films can withstand. Trial 4 was able to endure the highest amount of stress without breaking or stretching, as we can see from the graph. Trial 3 was the second most durable and was able to endure a decent amount of force also. And so if we look at trial 1 through 3, which are just the starch trials and no citric acid, we can see a correlation between starch content and mechanical strength. Whereas if we look at trial 4 and 5, the higher starch content resulted in a lower mechanical strength.
We also did a thermal test where we held our plastics over a flame and took a qualitative analysis of what they did. Here are some pictures of our different plastics. So as you can see, the citric acid did not appear to make our plastics more flame resistant. Trials 4 and 5 did visibly burn, but trial 3 also burned quite extensively, just a little bit slower than trials 4 and 5. And we're thinking this could be because of the higher starch content in trial 3, and trials 1 and 2 did not burn very much at all. Also, we did a pH test and a water resistance test, and we put our plastics in water and saw how it changed the pH and how much mass they lost. As you can see, the pH of the water after trials 4 and 5 significantly decreased, and this is because there was citric acid in those plastics, while trials 1, 2, and 3 successively became more water resistant and did not cause much change in pH in the water. Similarly, in the rate of mass lost after 20 hours of submersion, you can see that trials 4 and 5, as well as trial 1, lost the most mass, while trial 3 remained the most resistant to water. So our conclusions were that the cross-linked plastics were not necessarily more resistant to water. They did influence the pH of the water a lot more dramatically than we thought they would, while trial 3 actually resisted the water quite well compared to the other plastics, and it didn't do much to the pH, which was really exciting. And we also see that the modified plastics did actually take longer to degrade, which was surprising because they were also mechanically stronger, even though they felt a little bit tackier than the other plastics.
So we concluded that trial 3 was the most promising for a food packaging alternative. For one, due to its qualitative properties, which were very similar to that of polyethylene. It showed a reasonable degradation rate. It was mechanically very sturdy and able to withstand a decent amount of force. It was very water resistant, which is very important to the food packaging industry. And it also maintained a healthy pH level. So none of this plastic would persist in the environment or have any serious effects on the environment. So for future studies, we would like to look more into the formula of plastic number 3 and try to make it a lot more water resistant. We want to look into water permeability testing and also examine other cross-linking components such as whey. We want to test out how this plastic would work in solid items like cutlery, and we also want to work on actually making the plastic into a food wrapper and testing it in that way. We also want to look at antimicrobial and antibacterial components that we might add. We did do a seed toxicity assay. However, due to unforeseen circumstances, we were not able to finish it, and so we want to complete that at a later date.